So our first 5-5 video took a look just at the parent functions, if you will, of sine, cosine, and tangent. And the second part of 5.5 is, of course, transforming those just a little bit. So a few new vocabulary words that we need to know. Amplitude is what we would have before just referred to as dilation. And so how much is it stretching vertically when we talk about amplitude? We're dealing just with the height. The period is how long it takes to see that one full graph. And so there's a little bit of a formula for this. We can either take 360 degrees over b if we are in degrees, or 2 pi over b if we're in radians. And again, 360 in degrees is equivalent to 2 pi in radians, and that's what it took to see an entire cycle or full period of sine and of cosine. Phase shift is how far the starting point has shifted, and that is c over b. So these a's, b's, and c's come from this general form. If my graph is y equals, a is on the outside, which is where our vertical dilations always were. The sine of b, so something multiplying by the b, that period is really stretching it horizontally. So that's changing how long it's taking to see what those values are, and then incorporating a horizontal translation with respect to how long does it take to see a full cycle of it. So that's what makes this a little different than some of the algebraic functions we had looked at. So those are my a's, b's, and c's. This picture is from the book, just so that we have a nicer visual than what I had shown you in the first 5.5 video. So the amplitude here, this height, if I go from my axis to that maximum point, that tells me my amplitude. So it's from the center to the top or the center to the bottom. It's not from bottom to top or from min to max, if we're using the appropriate vocabulary. And then start to finish, my starting point to my ending point here is the 2 pi, this one's in radians, divided by b. And then there are a few extra notes here in terms of if the shift is positive, it's going to the right, and if it's negative, it's going to the left. So today we're not going to get into phase shifts, just deal with amplitudes and periods, but to recognize the A's, B's, and C's. These next couple pictures, again, just to have neat, clean pictures out of the book. Remember, at a height of 1, or this minimum at -1 here for sine, that happens at 90 degrees and 270 degrees, which are equivalent to pi over 2. That's the same thing as 90 degrees. And then 3 pi over 2 is the same thing as 270. And it's hitting 0 here at 0 pi and 2 pi, which is the same as 0 degrees, 180 degrees, and 360 degrees. The 1/2 sine is half the height that it used to be. So instead of being at a height of 1, it's at a height of 1/2. My zeros don't change, which is what's really nice about these trig functions, is that with all the x-intercepts that they have, it makes it easy to work with those values. 0 doesn't get cut in half to be anything else. It stays at 0. And so we're working with just the peaks and valleys with the maxes and mins. So the second one is just taking it from 1 up to a height of 2, because it has in fact doubled, and then something crazy happens in the third one. This, if you can see it, we've changed it a bit. So it's not just 2 sine x, but it's the opposite of 2 times the sine of x. And so the graph in the middle, where it showed at pi over 2, it was at a height of 2 instead of the height of 1. This point now has been reflected over the x-axis. It's making that flip up to down, which is what that negative out in front does. So same rules as what we've always had with our other functions, now just applying them to trig functions. And again, some things very similar. Thinking in terms of those vertical dilations, we're just calling it an amplitude now. Horizontal deals with a period, and then the idea of the phase shift are the translations that we would have had left to right. So just a different way of finding it. Same notes here for cosine, just showing that this more is the U shape than the S curve, because it starts and ends at its maximum instead of at those intercepts. So showing my shifts again, the amplitude picture is the same. Period is 2 pi over b, just as it was before. And the a's, b's, and c's are in the same place here for cosine as well. Y equals a cosine bx minus c. So a couple of graphs just to take a look to try to figure out what's happening here. The first couple just deal with amplitude, and then 7 through 16 deal with both or one or the other, I should say. Some of them only have a period change, but others have an amplitude change. So for something like number 1, and we'll just do a couple of these and we'll look at them in the calculator. This is where we have to know what the parent function looked like. And we are working in radians because it says 0 to 2 pi. So I have pi over 2, pi, 3 pi over 2, and 2 pi. And then I have a maximum of 1 and a min of -1. But if I look at my amplitude for this one, it actually has 4 times the sine of x down to -4. So if I scale by 1s on my vertical axis here, then my original sine function would start at 0, peak at 1 at pi over 2, come back to 0, swoop down to -1, and then go back to 0 again. That is just the parent function for sine. So y equals the sine of x is the one that I have here in blue. If I switch to green to graph 4 times the sine of x, this is like what we had set up above at 0. If I multiply by 4, it stays at 0. So all of those intercepts stay exactly where they are, but it's this peak here at pi over 2 that goes to +4, and then my minimum at -4 for 3 pi over 2. So now I just have a nice tall and stretched out sine function, which they do both continue in both directions. We're looking at just one period of them. So my amplitude, that value of a here, is just going to be 4. For number 2, it's exactly what we have up above. It's just going to be a height of 5 instead. And then for number 3, it's going to be a little bit shorter because it's 1/3 of what it used to be. So let's take a look at that one. And this one, again, is just a matter of scale it however it works for you. So I'll keep it about just as big. So I have pi over 2, pi, 3 pi over 2, and 2 pi. But if I have a height of 1 and -1 for my parent function, and then I'm just going to, as best as I can, count off by 1/3, then again, 0 up to 1 at pi over 2, down to 0, down to -1, back to 1, and then it's going to keep going. It would go back up to 1, and then back down to 0, and then -1, and on and on and on. So if it is 1/3 times the sine of x, then my zeros stay at my zeros, and now it is 1/3 of the height, so it is shorter, a little bit shorter and wider than what it was before. And so that's all that the amplitude is doing. So number 4, again, is just going to be even closer to the axis. 5 and 6 are flipping on me. So for number 5, the amplitude is 3. It's always the absolute value. But this one reflects over the x-axis. It has that vertical flip. So let me actually try this here in red. So my amplitude is 4. And so if I graph number 6 here, my zeros are going to stay where they were. But my +4 is going to flip to -4, and my -4 is going to flip to a +4. And so this is going to be what my graph would look like if I were graphing y equals -4 times the sine of x. So I have that vertical stretch first of the amplitude, and then I have that reflection component as well. And if you are ever unsure, all you have to do is check the calculator. Always, always, always just checking the calculator. We just have to make sure that we are in the right mode in order to do so. So for 7 through 16, the new component now is that we want amplitude and period. So since 7 and 8 just have period changes, I'm going to do that very, very quickly. So remember, it is y equals a times the sine of bx minus c. And for my period, I'm always looking at 2 pi divided by b. And so for number 7, that means that my period is equal to 2 pi divided by 2, which reduces just to pi. So if I were to take a look at this graph, I would see the entire sine curve between 0 and pi. If I looked between 0 and 2 pi, I would show it happen a second time instead of just once. And so that is squishing it. If I'm compressing it vertically, or I'm sorry, horizontally, I'm able to see 2 of my sine curves in 1 2 pi, if that makes sense. And so you're seeing it twice instead of just one time. So balancing that, taking a look at number 9. 9 says that we have y equals 3 times the sine of 1/2 x. So my amplitude is 3, so it's taller than what my other one was. My period now is 2 pi divided by 1/2. And so that actually gets multiplied. So 2 pi times 2 actually is 4 pi. So this means now that it's going to take me until 4 pi to see the entire thing. So I now have pi, 2 pi, 3 pi, and I'm going out to 4 pi. So my parent function before would have looked like this. So I would have gone up to pi over 2 and down and up, and that would be my sine curve. Now I'm saying that in order to graph this, to graph y equals 3 times the sine of 1/2 x, it is going to take me this entire length instead, and I'm going to reach a peak at 3 and then a min at -3. And just working through where those values might fall. If you needed to, again, check any of these on the calculator. I'm in degrees, so I'm going to switch first to radians. Start with what you know. So if you're most comfortable with amplitude, we'll go from 0 to 2 pi for my scale. And I can count off by pi's, but I'm going to stick with -3 to 3 for my y scale. And I'm going to put in 3 times the sine of 1/2 x. You can make it 0.5x. You can take it as just x divided by 2. Any of those would work. And if I take a look at this, it's taking its sweet time up there to peak, I'm going to see only the top half. I'm not going to see it finish in 2 pi. So now it's being stretched to take longer. If I need to go back to my window then and recognize that this is actually 4 pi in order to see the entire sine function, then I can see 2 animations that way. So the amplitude should be easy enough. That's just how much taller it's going to get. And then period, think of it as that horizontal stretch or shrink and that quick, easy formula for it.